Welcome everyone to the latest emissions analytics webinar. This time the topic is the effects of renewable fuels on combustion emissions. Before I delve into the slides, there are two things I wanted to say right up front. The first is that when we scheduled this webinar, we had no idea how potentially relevant and topical this was going to be, bearing in mind the German government's spanner that they put in the wheel of the European decarbonisation regulation, or at least temporary spanner, regarding e-fuels, synthetic fuels, which is one member of the wider group of renewable fuels. So this really now is a topic centre stage in the regulatory discussion in the wider societal decarbonisation. Now, today I'm not going to actually go into pure synthetic fuels in any detail, but rather focus on intermediate renewable fuels. But nevertheless, this topic of changing the fuel rather than changing the powertrain now has suddenly found itself centre stage, and probably quite rightly so. The second point I wanted to make is that we completely realise what a complex area this is. And on this call, there will be people who are much more expert than we are in the exact formulations of fuels, in understanding the in-engine combustion emissions, how the chemical reactions, how pollutants are formed. We are not trying to overclaim in terms of our understanding of many of those parts of the process. But what we are trying to share is what we do well, which is understanding what happens in the real world when you put these fuels in real vehicles, operate them in real ways. So the aim today is to share with you a number of examples of the work we've been doing, which has done just that on a variety of different fuels and vehicles, to add to the debate. And hopefully this will stimulate plenty of questions, and we do very much encourage you also to get in touch with us afterwards for further discussion. So to do this, we will follow the usual format of around 30 minutes of presentation, and then the same again in terms of questions. Please submit your questions from now on throughout while I'm speaking in the chat box at the bottom of the screen. Also, the slides and the recording of this will be available afterwards on our website, and we will do a replay of this later this afternoon, UK time, and also have a further session of live questions at the same time. So if you're unable to stay for the whole duration or have colleagues interested, please do join later on. So on that note, enough of a preamble, let's get into the meat of what we're talking about. And I will, sometimes I skip over this slide about our belief, but it is particularly relevant in this case. And it really boils down to, there's lots of great theory out there, but what really happens in practice? And ultimately, the only thing which really matters is if we deliver real reductions in pollutant emissions, real reductions in greenhouse gas emissions. So that's what ultimately we're trying to do, is to find out if these things do deliver in practice, just as we apply the same thing to different powertrains, to tires, whatever it is. So we are emissions analytics now almost exactly to the day 12 years old, a UK company, but operating all around the world on this important topic of independent emissions. We're not captured by industry or regulators or anyone else. We just want to find out what's really going on. And to that extent, we are open and do work with everyone up and down the supply chain. We've tested now thousands of vehicles, not just cars, trucks, diggers, cranes, marine vessels, skidoos, you name it, almost we've tested everything. And not just the tailpipe emissions, but increasingly the tires and the interior air quality. And we make this data available commercially. We are a commercial company, no secret about that. But this data is all therefore available commercially, and we also conduct lots of different test programs for people applying these very same techniques. Personally, I don't just sit there creating our test methodologies, but we try and make them as open as possible to everyone else. To that end, I've chaired 2 SEN standardization workshops, number 90, which led to a standard on urban NOx emissions from the tailpipe, and more recently SEN workshop 103, which recently published a standard for measuring vehicle interior air quality, primarily in terms of particle ingress. And finally, I'm an honorary research fellow at Imperial College London as well. So the agenda today, what I wanted to cover is a sort of recap of what the challenge is, and really trying to keep it at a high level understanding of what the issue is, rather than getting drawn too much into any one specific area. Then I wanted to talk about the methodology that we've developed, which we think is an innovative way of trying to understand what's going on in the real world. And then use that with some examples of renewable diesel that we've tested and renewable gasoline, not just looking at regulated pollutants, but also unregulated emissions as well. And the final bit would be to look at the issue of the actual chemical composition of the fuel itself. So looking beyond the basics of, is it EN 228 compliant or not, actually in much more detail than that, and how that might help us explain the provenance of these renewable fuels. So moving into what is the problem? Well, we're obviously, almost goes without saying, we're trying to reduce climate change related emissions and also improve air quality. The issue with renewable fuels, which is the flip side, of course, of the opportunity, is that they are there first and foremost to reduce life cycle CO2 emissions, so to contribute to the climate change solution. But the question relating to that is, how much do they actually reduce CO2 in practice? They often sound good, and from a marketing point of view, they, what's not to like? But do they actually reduce, or by how much do they actually reduce in practice? So can they be a material contributor to our decarbonisation, or are the reductions too small, too expensive, too difficult, that we just have to go straight to battery electrification on the assumption that that is free of emissions, which obviously it's not, but that's a topic for another day. One other aspect of renewable fuels is maybe they reduce tailpipe emissions, but maybe they lead to increases in certain pollutant emissions. So what might we not know about hidden other increases in emissions? And there is also the important distinction between, it may be okay to increase emissions a little bit if it's from a very low base and it still remains well within some regulated limit or health threshold. So the question is, does it, if where there are increases, does it take us above any existing limit values? And similarly here for unregulated emissions, there are obviously no limit values, obviously, but do they lead to some worrying levels on some other criteria? And also, can these have a direct impact on air quality and on health? And how do we understand that? So that's the issue at a very high level. What is a renewable fuel? We need to be clear, and that covers a very diverse group of products. And it's an evolving definition as well. But the best way I can describe it right now is that these are fuels which are produced from renewable sources rather than fossil fuels. And actually, I should even be clearer than that to say produced in part from renewable resources, because many of these sort of first, second generation renewable fuels still have a fossil fuel component, potentially significant fossil fuel component. So it has some element of renewable non-fossil fuel component in them. And examples would be, for example, bioethanol. So within that, the E10 we now find in the UK and some other European countries, that it contains bioethanol blended into gasoline, and where that ethanol is typically grown from crops. Biodiesel would typically use fats, which substitute through transesterification, substitute some of the fossil fuel components, and those fats can come, for example, from waste cooking oil. Biomethane, which is one that we've done some testing, for example, on heavy-duty trucks, converting those to natural gas, where a proportion of that natural gas is biomethane, typically comes from the breakdown of organic matter such as anaerobic digestion. And those in a sense could be described as maybe the earlier generations of renewable fuels. Then we get to more advanced biofuels, and HVO is probably the one getting the greatest profile at the moment, which is sometimes called hydrotreated, other places called hydrogenated vegetable oil, and that we will look at specifically in this presentation. Then going to the outer reaches of renewable fuels, we could include green hydrogen in this. So hydrogen created from electrolyzing water. That is renewable in the sense of it's a non-fossil fuel origin. Obviously, there's lots of different grades of hydrogen, a whole rainbow of colors of hydrogen, but green is probably the benchmark of low CO2. And then finally, as we talked about right up top, the synthetic e-fuels question, for example, creating gasoline from methanol, which itself is created from a combination of sequestering CO2 from the air, combined with green hydrogen to create a near zero CO2 liquid drop-in fuel. So that is, and I realize that is highly simplifying the matter, but just to give an overview of what we're talking about in the landscape, I think that is a reasonable definition of what renewable fuel is. And the challenge related to this is that we're essentially, for the intermediate ones, inserting some, quote, bio components into fuels, which may change the combustion characteristics for good or bad, and may change the energy density, often lowering the energy density, but also have an effect on the efficiency of combustion. And different combinations have different effects. It's not always in one direction. But nevertheless, this change in chemical composition can lead to an alternative mix of tailpipe pollutants. Point one, and that's sort of the air quality related element of it, but also the CO2 reduction potential of these fuels doesn't tend to manifest itself at the tailpipe, though any changes in CO2 tend to be small. The CO2 reduction exists upstream in the supply chain. And so through using waste material or crops, which suck up carbon as they grow. And therefore the verification, we can't go along with a piece of PEMS equipment and go verify that CO2 reduction because it exists up the supply chain. But nevertheless, verifying that carbon reduction is really vital to understand the benefits of these fuels. And then also linked to it, which we won't cover today, is the questions of, this might work at small scale, but can it scale to anything that will help at a system level and economically as well? So that's the problem. Our concept for how we approach trying to test for this and understand it is what I would describe as holistic and comprehensive. Holistic in the sense of considering all the different vectors for the car creating an environmental impact, and comprehensive in the sense of trying to understand, as comprehensively as possible, what the pollutants are. And this picture sort of neatly encapsulates what we do. So we are testing on the road, real cars on the real road, real drivers, real routes. Top right, we are obviously looking at the tailpipe, but as I will show, we are looking at an increasing number of pollutants from the tailpipe. There's tires as well. Now, tires is not relevant to today's presentation, but tires shed matter and off-gas VOCs, etc. So they are vitally important in the whole environmental impact of vehicles, and actually does have a tangential relevance to this topic, where substitute materials are being put in tires, for example, soy-rich tires. So in a sense, renewable tires, if you like. So we're not covering that today, but it's why you can see it's an integrated part of our approach. Then we have vehicle in-cabin air quality. It's a massively underrated issue of, when we focus on air quality externally, how much actually gets inside vehicles and stays caught up inside vehicles. So in a sense, any pollutants that come out of the tailpipe can also be recycled into the cabin as well. And the final one is understanding the composition of the fuels. So for today, it is basically top left and top right that we're focusing on, the actual fuel composition and the tailpipe emissions themselves. And the equipment we use, and I'm going to skip over this first bit relatively quickly. Most of you will be familiar with the standard regulatory compliant PEMs measuring CO2, CO, NOx, etc. Also with particle number integrated and in real time, at 1 Hertz, OBD logging, etc. But to that, we have created a patent pending system which allows us to sample exhaust gas onto a range of thermal desorption tubes in real time, or as the vehicle drives around, I should say, using a proportional dilution system, which allows us to capture that and derive from it distance-specific mass emissions. To measure what's actually on the tube, we use a two-dimensional gas chromatography system with mass spectrometry from Marks International, and a modulator from Sepsolve Analytical, we use various different, for the purposes of tailpipe emissions, we thermally desorb the gases from the tubes into the 2D GC, and that allows us to do a profiling of the organics in the tailpipe or in the fuel far beyond the standard tests. There is one exception to that, formaldehyde, which is far too volatile to be workable on a gas chromatograph. So we use a DMPH derivatization cartridge in our tailpipe sampling, which is then analyzed using liquid chromatography as shown. And when we thermally desorb a tube, this will give you an example of what we see in the two different time dimensions of separation, and then the height of the peaks here. So each peak is one compound, and the height is an approximation to the mass present. So you can see typically in the example we are seeing hundreds of compounds off any particular tube, but in wildly varying concentrations, and the sensitivity of this system is at least at the ppb level, if not lower. It gives us an absolute wealth of information, but to make any sense of it at all, we have to group all these hundreds of compounds into some meaningful functional groups. So alkanes groups or terpenes or aromatics, which as shown on this chart tend to have common health and environmental effects, not consistent, but they associate with one another. And I'll come onto that a little bit more later on. So that's how we do it. So let's move on now to looking at some renewable diesel and then some renewable gasoline. So the renewable diesel, this I'm sharing part of the results we did from a very interesting test project with Thames Tideway. For those who are not in London, Thames Tideway is a massive project to build a big new sewer across London. London sewers were built in Victorian times and is in desperate need of this big new sewer, which is getting close to completion. But in excavating this, it created huge amounts of earth and other waste that needed disposing of. And there was a question about, or a twofold question. One, was it better from an environmental point of view to ship it along the Thames on a barge or stick it on lots of trucks on the road? That was question one. Question two was, and is it better to power these vehicles by standard diesel, road or marine, or better to do it with HVO? Now here I'm just going to share the second part of that, so the standard diesel versus HVO results. And in this case, this was only on the truck part of it. The HVO in this case was provided by Green Biofuels, so it was their Green D Plus product. And the test was essentially a control test of shipping 500 tons of payload between Deptford and Woolwich in London, as shown in that in that map. And this testing was done over a number of years and completed last year. So focusing just on the road, the truck results, here we can see the results for the, so this is the same route, and it's the average of the payload, the laden legs, and then the return leg as well of the truck when empty to go and pick up some more stuff. And the truck goes backwards and forwards multiple times. So we've got the fuel consumption, CO2, CO, basically pretty much all the regulated pollutants there. And we've got the B7 standard diesel and the HVO, and where the variance cells are coloured in indicates whether there's statistical significance in the results. So what this shows is that there was a statistically significant reduction in NO, NO2, and NOx with the HVO. So pretty much a halving, statistically significant halving of the NOx on the HVO. But there was an increase, statistically significant, in particle matter. So a mixed picture there. In terms of mitigations, I mean, or the absolute levels we're seeing, particularly on the particles, it's well below. If we converted that to per kilowatt hours, it would be well below even the light duty, or in per kilometre, it's well below the light duty limit. So even though, this is my point I made earlier about, even though it may be an increase, it is still not necessarily at a problematic level. But nevertheless, that is an area that may need to be looked at in more detail to mitigate, but we are crystallising some good reductions in NOx there. But then there's the question. So that sounds, there's some benefits there definitely to be had, and there's some issues on the particle side to look at. But we need to look at the question of the provenance of these fuels. So were these fuels of the true origin? So this is now looking at, we tested a number of different HVOs from different sources and looked at the chemical composition of them. And I should just be clear, this was not linked to the tideway test. This was a separate piece of work and taking HVO from multiple different sources. And it's trying to get to the bottom, of when you buy HVO in the market, does it live up to the billing in terms of its credentials? And here, this is just a chromatogram here, which shows the typical, when you do a liquid injection to the 2DGC, what the chromatogram of a typical fuel will look like. And what that really is, it's a chemical fingerprint. So thinking about the idea of chemical fingerprint, we can look at the actual results here. So there's 4 different types of HVO, so different ones from different sources, and compared to a B7 diesel reference. And to keep things simple, what I've shown a number of metrics here, which is the number of organic compounds that we found and identified in the sample, and then the proportion of the area under those peaks on the chromatogram that go in the aromatics and PAH group in percentage terms, how much are in the alkanes group, and also looking at it in terms of what proportion are oxygenated compounds. I know that does cut across the other 2 categories to some extent, which is why it doesn't add up exactly to 100%. But looking at the oxygenated percentage is also quite insightful. So what we see is that there's typically, we're talking in the hundreds of compounds, but it's the fossil fuel B7 diesel which has the highest number of compounds at 669. I mean, it should be noted that it goes to show how many organic compounds there are in these products anyway, and the complexity of understanding them. But what jumps out here is that of 4 different HVOs, so things marketed as HVO, 1, 3, and 4 are pretty similar. They're dominated by alkanes in the mix. They're in the sort of 200 to 300 level of organic compounds. But HVO2 stands out as quite different from the others. And these are all legal to sell. They all meet the relevant regulation, apparently all meet the relevant regulations to be sold. So HVO2, not only has it got more organic compounds and a much higher percentage, 13% of aromatics, and much higher proportion of oxygenates as well, which actually makes it look a lot more like the standard fossil fuel diesel. So this would lead us, and I've simplified this example to make the point, but this would lead to a hypothesis that HVO is actually much more primarily fossil fuel B7 diesel being passed off. Yes, maybe with some additions, some proportion of HVO possibly, or something else in it, but it clusters much more with the B7 reference diesel than it does with the other HVOs. We also then looked between the HVOs as to, well, with HVO2, which is the blue blob on the principal component analysis chart, we tried to understand what was it that made HVO2 different from the other HVOs. And so we ran a PCA, effectively a deconvolution analysis, just to trying to understand differences. That it is cyclododecanol, which is the primary differentiator of that. So HVO2 had less of that in it, significantly less. Now, interestingly, cyclododecanol is quite an important compound in that it is a known aquatic toxin. So the proportion of it in these fuels, it is a relevant environmental factor. But actually HVO2 in this case has less, the thing which is distinctive, it has less of that in it than the others. So what we conclude, or very strong hypothesis here, is that HVO2 is in some way, well, it is, I think the most generous thing you can say, it's not as HVO-y as the other HVOs. The less charitable interpretation would be that there's some degree of fraud going on potentially with it. But let's back up and not be quite as controversial at, and simply say it is likely that the CO2 reduction credentials of HVO2 are not as good as the CO2 reduction credentials of the other HVO. Therefore, if we are to scale these renewable fuels as solutions, then we need to understand these differences and bring about a much greater transparency and standardization about the composition. So that's on the diesel side. Let's move on to gasoline. So for this, the main data I want to present is from a recent test program we did last October, which was looking at the difference between E0 and E10 in passenger cars, recent model year passenger cars, in real world on-road driving. And the fuels here were blended specifically to EN228, this is all on the road at the same time of year, same conditions, on our standardized EQA test route, which is made up, it's about 3.5 hours long, made up of a combination of cold start, urban, rural, and motorway driving. And firstly, let's look at the regulated pollutants by vehicles, focusing on carbon monoxide and NOx. And here here we're showing in the shaded boxes the directional. So green is good in that it's lower, and pink is higher. So what we actually see is quite a good level of consistency in the direction of these pollutants between the different vehicles. The average reduction in carbon monoxide was 31%. And the increase in NOx was 21%. However, it must be flagged that that absolute increase in NOx was small, i.e. from a very low base, and even we're on E10 was 90% below the regulated limit. So where I say EF, that is the exceedance factor, the ratio between the real world emissions and the regulated limit, which in this case for these Euro 6 diesels would be 60 milligrams per kilometre. And also, I mean, the CO is well below in all cases as well. So here, so we've got, I mean, but we have to remember, gasoline vehicles don't generally have significant gaseous tailpipe pollutant problems anymore. So we're arguing about making slightly cleaner or slightly dirtier something which is already quite clean. But nevertheless, that's what we're able to measure and show. But then let's look at some unregulated pollutants using the GCMS approach. And now, why are these important? So these are not regulated, and actually, sadly, they are not being slated for inclusion in the light-duty Euro 7 either. So why these unregulated pollutants, particularly VOCs, matter is that they have an ozone formation potential, which can lead to increased smog levels, which we saw during COVID as the amount of NO2 in the air was reduced. They also have a secondary organic aerosol formation potential as well. And the four areas I want to look at is firstly formaldehyde, which in terms of human health is an irritant. It does bad things to your lungs, is a carcinogen as well. And but it's not so much of a problem for other environmental reasons because it is non-accumulative. But other aldehydes, including acetaldehyde, these are can damage organs, can create inflammation and pain, carcinogenic, heart disease as well, and for plants can inhibit growth. Then I picked out toluene as a relatively high concentration organic compound in there as well, which is an irritation to skin, eyes, throat. It causes damage to some organs and a possible neuro and reproductive toxin as well. It's also moderately toxic to fish and plants. And finally, nitrous oxide, so N2O. Now, obviously, it's used for some medical purposes as well, but in higher concentrations can lead to unconsciousness and other longer-term effects. And was a part of the Euro 7 discussions, not just because of its powerful greenhouse gas effect, about 250 times CO2 equivalent, but also can act as a pollutant, air pollutant in the upper atmosphere as well. So those are the four I wanted to pull out, although we do have the full chemical profiling of typically about 400 or 500 compounds in each exhaust. So here we are looking at this. So this is summarized by vehicle across the combined cycle for those four different vehicles that you can see. And what we see overall, and just at the macro level, looking at the color coding, is that there's a lot of variability between the vehicles and between the pollutants as well. And so, I've given the mean figures there, that those means are disguising a lot of variation, but on average, there is a 18% increase in formaldehyde, but a 20% reduction in the other aldehydes. It's toluene that stands out as almost doubling, and big increases on three of the four cars. But interestingly, N2O, it doesn't, and maybe not very surprisingly, doesn't make a great deal of difference one way or the other. And there are two cars there, the Peugeot 2008 and the Citroen C3, with the same base engine, but with different power levels, and therefore different calibrations, lead to quite different results. If we then look, though, cut the same data, but looking at it by the different parts of the cycle, averaged across the four vehicles, we actually come to a much more consistent position. And where you've got the formaldehyde is up in all cases, as is the toluene. So at that level, and there are obviously the mix effects which are creating these averages. But you can see particularly, say, in the cold start, the effects on the formaldehyde and toluene, but reduction in aldehydes. But on the motorway, there's increases in on all pollutants, and indeed on urban as well, and almost on rural too. So we can cut that data in lots of different ways. But that was comparing E0 to E10, and we're in many countries in Europe increasingly at E10 already. So what happens if we push that 10 to a higher number? And in the last bit of this presentation, we'll just quickly look at some work we did with Volkswagen and results they presented late last year at FAD in Germany, which was to look at some alternative blends, including E20. So we tested 4 different types in the end, which you can see on this slide, on a Euro 6 D-Temp vehicle around Stuttgart in Germany, looking for the effect on regulated and unregulated pollutants again. So on the regulated side, and you can see in the key, it's the far dark blue bar, which is the 20, that you do get lower CO2 emissions and particle number emissions as the ethanol proportion increases. But the CO emissions do increase somewhat on the E20. So a pretty good, not quite unambiguous, but certainly on the CO2 and the PN side, a clear trend of reducing emissions as the proportion of ethanol increases. But looking at the unregulated side, looking at formaldehyde specifically, split between the different parts of the cycle, and then I put in the aggregated of the oxygenates on the cold start cycle. In all cases, or almost all cases, we are seeing the highest formaldehyde and oxygenate levels on the E20 level. So that, in a way, that is in line with the concern from the chemistry of the combustion, whereby increasing the amount of these oxygenates in the fuel may well lead to the formation of formaldehyde and other aldehyde emissions in the tailpipe. And so we may well and are likely to find ourselves in the position of trade-offs between the CO2 reduction credentials and some increase in the air pollutants. However, that's where we then need to study as to whether these increases are actually very small in magnitude, below any levels of concern, and so are actually all in the acceptable range. So in summary, and I realize I've gone slightly on, but I had quite a lot to cover, but we still have good time for questions. So in summary, well, firstly, the combination, putting PEMS together with 2D GCMS, we found is a very powerful way of understanding fuel properties and tailpipe emissions. And in a sense, this presentation is almost just scraping the surface of the detail available through the test data we collect. And renewable fuels can definitely make some reductions in regulated pollutants. The ethanol in gasoline may lead to certain increases in certain aldehyde and other emissions, but it's essentially overall the mixed picture and very vehicle specific. And so as we focus on this more, engineering calibration optimizations may well be able to mitigate this, but it does need to be studied. Within the macro context, we do have to face the concern that everyone is going to want these types of fuels now. And particularly if Germany is successful in getting a carve out for certain types of fuels, the supply pressures and therefore the fraud risk will increase. So understanding and verifying the credentials of these fuels is important. Fuel fingerprinting is a way of doing that. Now, this may be seen, this concept may be seen as a burden to the renewable fuels industry, but I would say it's actually absolutely vital. What we don't want is a Dieselgate-shaped scandal a few years' time where these fuels have been adopted and then the market has been undermined by certain less than genuine fuels. So getting this verification of provenance right from the start and understanding the tailpipe emissions from the start is really important. And by doing that, hopefully by demonstrating genuinely low emissions, this sector will thrive. So on that note, thank you very much for listening. And I can't finish without saying that, as I said at the beginning, all this data and much else is available in our subscriptions database. It's available and it's great for benchmarking, R&D work, and we also offer testing services using the same technology as well. So thank you very much for listening. I do appreciate your time as ever, and we will come to questions shortly. Thank you. Okay, so do keep your questions coming in. I'm going to start scanning through them, so bear with me for one moment. Okay, so the first question is, how do we define renewable fuel? The point is, from a media perspective, this implies that an internal combustion engine car burning this fuel has no impact on the environment. I mean, this is a really good point, and I tried to set out at the top, in a sense, what is the practical definition of renewable fuels, and they come in different shapes and sizes. But the point, Paul, you're making about it does make the implication that you can suddenly turn an ICE vehicle into a zero emissions vehicle. That is the implication, and that is an implication we do need to be really careful about, because if these fuels are oversold, the truth will catch up with them eventually, and it'll create another problem. What the automotive transportation sector does not need is another scandal. So what I would say from this is it's absolutely vital that these fuels make really clear what they are offering, and we can't wait for new regulations to come along, because essentially we might be waiting for Euro 8 and beyond. Euro 7 is unlikely to be made more stringent than the European Commission's proposal. If anything, it'll be made less stringent. So we're not going to get significant profiling of these unregulated pollutants. And there are some for the heavy duty regulations. I'm aware of that in terms of formaldehyde and non-methane hydrocarbons, but not to the level we've looked at this morning. So I think the fuel producers or the vehicle OEMs need to be really proactively transparent to make sure we're not overselling these. Underselling would be better than anything. Saying it'll give a 20% reduction in something and overachieve is much better than claiming an 80% and then being found to be playing fast and loose. Next question. Sustainable implies you're doing this without compromising the next generation's ability to make renewable fuels. Well, I mean, there are different levels of sustainability here, and it is probably the case, although we again may be able to argue it for a long time, as to what the current renewable fuels are, which blend in waste products or other grown components, versus those longer term renewable synthetic fuels. So where we get to green hydrogen or methanol to gasoline, there is less of an intergenerational issue, where the issue there is simply we have to have enough green electricity to power the process. And let's say, for the sake of argument, that comes from nuclear fission, then there isn't really a intergenerational contention for the fuel resource. The only intergenerational fight then would be for what to do with the nuclear waste. And that remains an unresolved problem, although the nuclear waste is in relatively small volume. But I like the question about the intergenerational question. It is a relevant one. Okay, moving down the question. Point about saying verification is not difficult. It is well defined in EU regulation. It requires effort on the whole cycle and may be complex, but not necessarily difficult. Interesting philosophical definitional question here. And it is, in a sense, it is conceptually possibly quite straightforward, but it is practically very difficult. And I think it's fair to say EU regulation of recent years comes with certain history, and Dieselgate is a very good example of high intent being undermined by deliberate omission in the execution, i.e. stringent standards were set, but then no one looked as to what was really going on in practice. So, and apparently the Euro regulations were drafted, they were in EU regulations. Apparently it was all clear until it wasn't. And so some combination of loopholes and not being attentive to what was happening in practice led to Dieselgate. And that is the shape of problem that I'm concerned will recur in this area unless we do something about it proactively. So it's not sufficient. So it's obviously very helpful that there are things written down in EU regulation, but that is not sufficient. proper surveillance and enforcement and testing in the real world is necessary to make sure it works. There's a comment about Zemo's renewable fuel assurance scheme is there to address the traceability issue, auditing the supply chain all the way from the feedstock. And Zemo, for those who may not know, as that was the low carbon vehicle partnership in the UK. So it's a sort of pseudo government funded organization around low carbon decarbonisation. And I will put my neck out slightly on this one and be ready to stand corrected, is that the fuel assurance scheme there does exist, but essentially it is a paper exercise. And so it relies upon declarations from the supply chain, and that paperwork is checked, but I'm not entirely clear whether that paperwork is checked for, or whether there is any system currently yet for checking the veracity of the paperwork in the first place. Maybe there's been some progress since I last looked at it, but that is the issue, and that, without wanting to go too wide, is the problem with a lot of the ESG initiatives at the moment. They are paper exercises and not attentive enough to what does that paper actually represent? Does it actually represent a real good thing that is being done such that it actually does lead to some environmental improvement? So I stand here to be corrected if I'm wrong, but I think it is just a paper exercise at the moment. Very good question here. Is it really possible to have a CO2 neutral emissions chain for the holistic production of e-fuels in this decade on an industrial scale? I suspect the answer is no, but that does not mean e-fuel should be written off. Far, far from it, because actually that question comes down to the scaling of a green grid, electricity grid, and that will take time. But that is necessary to make sense of battery electric vehicles, to make sense of hydrogen for heavy duty transportation. So if there is one policy the government should be following with all effort, it is decarbonising and scaling the grid. And then e-fuels may well become a very significant proposition in the next decade and beyond. As it stands at the moment, without some significant technological breakthrough, I personally find it very difficult to see how that will happen without major expansion of nuclear fission, both sort of scale nuclear fission and the small modular fission as well. I realize, there will be some who say scale wind and solar, and yes, absolutely we should and are and need to go faster, but you need to balance that with a significant consistent base load as well. So I think the nuclear is the bit that we're not doing at the moment, and if we do, then e-fuels can become a very significant thing. But as the question implies, not this decade, next decade, I would say. And we should always remember, after the fuel crisis in 1973, France managed to move its almost entire entire electricity production to nuclear in a period of about 15 years. So it can be done. I think it was about 60 nuclear reactors that were built, and means that France still has one of the very greenest grids in the entire world. So it can be done if we set our minds to it. And actually, I think in answering that one, I've answered a number of others as well, from Stefan, and so hopefully that covers that off. Moving down the list, and do come in with any, we've got a few to get through, but do keep them coming. What was the Euro level in the truck in this experiment? I believe it was a Euro 6 diesel truck. Yes, thank you, Tom. Thank you, Tom, for contributing. So I got that right. Thank you. on slide 18, what is the NOx concentration in the ambient air during these measurements? I don't know off the top of my head, but I will come back to you on that one. I don't know, Tom, you may know that off the top of your head. A good question here. How can we launch and legally approve all these fuels knowing that no one knows the exact composition? Well, we don't know the exact composition. If we focus on the word exact, we don't know the exact composition of the diesel and the gasoline that we get at the pump anyway. All we know is that they conform to the EN standards. Within that, there can be quite a lot of variability. So if I fuel up with E10 gasoline, that could be anything between 0 and 10% ethanol. And there's no disclosure of what the composition of the fuel is on that day. Similarly with the 7% bio component in diesel. So there's already variation, and the EN standards give a sort of minimum assurance as to what's in the fuel. And I think you probably would be overdoing it to need to know and disclose the exact composition of everything. But what we're suggesting is you need to have somewhere between where we are currently and full understanding, which focuses on certain components in the fuel that are relevant to increases in certain tailpipe emissions, or relevant to understanding the provenance of it. And that maybe that should be included in the European standards, or maybe that could be dealt with by voluntary disclosure by manufacturers, maybe to some SEN standard, for example. So I think there's a happy medium to be had there, which is more than we've got today, but less than having to try and share hundreds and hundreds of different compounds and compare them between fuels. To the question, do the HVO samples all comply with EN 15940? Yes, I believe the answer is they're all ones which are legally sold on the market at the time, which was just over a year ago. We've covered quite a lot of these questions. Are all the vehicles in the gasoline test Euro 6? Yes, they're all Euro 6. One of them was a 2020 model year. The rest were 2022, so all very recent. Question: I think N2O and formaldehyde are now targeted in Euro 7. The formaldehyde, I believe, is only on the heavy duty, not on the light duty side. N2O is, but yeah, it is a shame that on the light duty VOC side that not much is being proposed, but it is at least a step in the right direction on the heavy duty side. Okay, I'm taking my time because there are so many questions coming in, and thank you very much for the volume of questions to cull through them. Oh, now that's a very good question, which I will flag it purely as a good question rather than one I actually have an answer to. Is there any impact on engine deposits or impact on any after treatment systems? All we can say is during the period of the test, there was no observable difference in the performance of the vehicle from a either sort of power performance point of view, or indeed, the frequency. Well, actually, on the truck side will be frequency of regeneration, not on the gasoline vehicle side. But beyond that, in terms of for these tests, we were not boroscoping engines and looking at deposits, unfortunately. But that is a very good idea for future work. A question here: do you have any explanation as to why your real-world HGV test is quite different to the standard certification test cycles, which tend to show only small NOx change but considerable particle mass with a paraffinic diesel? Well, I think this goes to show the importance of the difference between the certification test and real-world testing, because this was ultimately real-world testing backwards and forwards on a road with payload. but also I suspect, although cannot prove definitively, that it may well speak to the differences in or the variability within the generic groups of fuels that we talk about, how much chemical variability there can actually be. So that's my strong educated guess, even though I can't definitively prove that. Have we tested CNG and renewable methane? Yes, we have. We did quite a significant project with Air Liquide on this, together with various fleets, including John Lewis, who have rolled out CNG on quite a bit of their fleets. And we measured a lot of different pollutants over a long period of time, came up with some interesting results, which, to paraphrase, I think would be, if you just switched from diesel to CNG, the environmental improvements were small, few benefits, few downsides. The big difference was if you, instead of going to fossil CNG, went to renewable methane of proper provenance, and that gave you a significant reduction in CO2. So a switch from diesel to CNG probably wasn't worth it, but from diesel to renewable was vital. But again, it comes back to our question of provenance. We knew in that case that it was from a very robust source in Air Liquide, but that was vital to the overall calculus of saying that it was beneficial. Okay, we've got a couple of minutes left. I will, where I've missed questions, I will try and come back to those after the session, or do feel free to chase us up. I think this clearly goes to show, this is an extremely complex area, and this is a subject we will return to many times, no doubt. Maybe we will end on a slightly good point, to say that nuclear is not renewable, and that is absolutely true. It is absolutely true, but what it is very, very low CO2. I didn't include mention of nuclear on my definition of renewable fuel, so I think I can be excused, but I did mention it in my answers, and it is absolutely true, but it comes down to, at a very, very macro comment, that our whole society is built upon fossil fuels. And if we are to truly decarbonize that, we need to find, at that scale, an alternative energy source to fossil fuels, and nuclear has to be there. It has to be a significant candidate, even though it is totally not renewable. It is non-CO2 or very low CO2. One or two questions of clarification that people have asked. For example, what after treatment system in the exhaust did the truck have running on the HVO? In this case, it was a Euro 6 truck with SCR and DPF, which probably accounts for the relatively low absolute numbers. And on that note, it is worth emphasizing that in most of these cases, it's certainly arguable that the absolute levels of these pollutants are really low on either fuel. And actually, in a sense, that is a good thing. And so why present these results? The answer to that is, all these new innovative fuels are being introduced to the market, and there is, in a sense, a burden of proof on these new fuels to show that they are not significantly worse than the existing fuels. So in innovating, we're not doing any harm or any additional harm to the environment. Ideally, the pollutants, regulated and unregulated, would be less than the traditional fuels, but at least to know that they are not in significant sense worse than the existing fuels is a really important point of establishing the credibility and the longevity of the renewable fuels sector. There was a question also, just to clarify, that where we were sampling the emissions. In all cases, these are tailpipe emissions measurements, not engine out. We've not done, for the purposes of this, any before and after the after treatment systems. I do note also that there's been a lively debate in the chat about the merits of hydrogen and ammonia as potential fuels. I would encourage, it's been an interesting discussion. I'm not going to go through all of it. I'd encourage you to read it. But we do test those sorts of fuels as well, where hydrogen is introduced into the combustion in some way, and also ammonia engines too. And we can apply these same techniques to get a really good profiling of what goes on with these innovative types of powertrain fuel combinations. There's a number of questions around the HVO side, which is understandable. I mean, the first one was around the sources of these HVO. Now we're deliberately, because actually it's not, the purpose of this is to identify exactly where who the suppliers were, but they were sourced from multiple suppliers. But they were multiple suppliers who are active in the marketplace, selling supposedly quality, legitimate, compliant HVOs. As to the specific question that was asked about, have any additives been added to the HVO? Certainly not by us. What we've done is taken the products as sold in the marketplace by these various suppliers. Then into there are questions about the repeatability of our testing, and I think it's specifically aimed at the unregulated pollutants. In terms of the regulated pollutants, it's very much in line with the experience that many others have had, and has been studied by the JRC in terms of the repeatability of PEMS measurements for NOx, which is typically sort of plus or minus 25% test to test, much lower obviously for CO2. But if the question is relating to the unregulated pollutants and the thermal desorption tube method, as a new approach to this, we asked the National Physical Laboratory in the UK, which is the UK's metrology lab, to do a specific study around the work we were doing, and specifically around the repeatability of the quantification of these pollutants, and we did it as focused on tire wear repeatability in the first instance, but those results are likely to stand well for this. So being clear, we haven't done the study specifically for this. But what it highlighted was that the main source of variability and these measurements was in terms of drift on the mass spectrometer. And as a result, the use of internal standards and effectively the calibration of the mass spectrometer is the central feature in achieving good levels of repeatability. And I would expect to see similar levels of repeatability, therefore, on these measurements than from the specific study that MPL did, and probably in the order of 20 to 30% variability at the individual compound level, which are typically being measured at parts per billion concentrations. When aggregated up into functional groups, I would expect that variability to be less, although that exhaustive study hasn't yet been done. But hopefully that gives a feel for the variability we would have, but also the approach we are taking to try and understand the variability on this new method. And there was also another question specifically on how many samples in each case we are analyzing. And it does vary depending on the experiment we're trying to do. Typically, it would be a minimum of three repeats that we would do. And in all cases, we have found very good, consistent results. So my interpretation of that is when you're doing multiple repeats of the same thing in a short space of time, you get very repeatable results. The great danger is if you do them spread out over greater time, where the spectrometer has a tendency to drift. That is where you need to understand and correct for that. A comment made is, what feedstock was being used in producing these HVOs, and saying that would be relevant for the emissions. I think that's true, but only to a certain extent. I mean, these are HVOs that are supposedly compliant with the required standard, and I do not think it would explain the variability of HVO2 compared to 1, 3, and 4. That is much more likely to be explained by something in terms of its mix and its similarity to the standard diesel. There was a question about asking about the information on the barge, and that may be a subject for another day. But given the question's been asked, I'm very happy to give sort of some headlines. And the contention was the barge versus truck comparison. And the suggestion was that the barge would be much lower greenhouse gas emissions, but much worse air quality due to the lack of after treatment system. And that's true in some important respects. But it is very dependent on the greenhouse gas side on two factors. Firstly, the payload that the barge is pulling and the speed at which it is pulling it. So the ideal combination for CO2 reduction is very heavy payload and steaming very slowly. If you do a lighter payload and steam fast, then the truck wins hands down. And it's an interesting comparison. We also did some separate work looking at whether there was a big difference between Euro 5 and Euro 6 trucks. And indeed, Euro 6 trucks put a much higher bar of comparison, particularly on the air quality side, compared to the barge. But in greenhouse gas terms, in summary, as long as the barge is heavily loaded and chugs along slowly, it is a lot better for greenhouse gases. So in a sense, it matters commercially. How much does traveling more slowly matter in financial terms? On the air quality side, also the contention is right. Without the after treatment systems on the barge, it was much worse, particularly than Euro 6 trucks. But you could say that, in the middle of the Thames, and particularly as it widens out, how much of an issue for air quality is that? So we can have an argument about that. But where we can be certain there is an issue is when the barge is in the dock. And often it is idling for long periods of time when it's being loaded up. And that is really poor. It doesn't require a PEMS measurement unit to realize the high concentrations of particles and NOx in the immediate vicinity. So that's the headlines, and I'd be very happy offline to share more information, but it also may be something we come back to on a future webinar. There's a good question here saying, given the current debate about the ULEZ expansion, it would probably be more useful to highlight with data the impact of diesel locomotives, river vessels, and older buses with zero after treatment, which are often hundreds of, thousands of times higher on pollutants than Euro 6 versions. And actually, that's absolutely right. To make that sort of argument and to look at, what interventions in policy we should do to address the London fleet, say upgrading Euro 6 vehicles maybe to Euro 7 vehicles in a few years' time, or changing the fuel on Euro 6 vehicles to make them very slightly cleaner in absolute terms, that probably isn't the right policy intervention from an air quality point of view. Absolutely. Improving London and other cities' air quality is absolutely about getting the dirt or older vehicles off the road as quickly as possible. Now, what does older vehicle mean? I would strongly argue that it can affect vans right up until 2020, So the pre-RDE vehicles that were subject to, the whole Dieselgate discussion. So the effective vehicles can be much newer than you would expect. On the car side, it's probably more like 2018 that most of them would be pretty clean after that. But I would concur absolutely. But the point of this presentation more is about what do renewable fuels need to do to evidence their credentials, to allow for a good functioning of the market, so people have confidence in these fuels, and also that we don't wake up with a Dieselgate type scandal a few years' time where we've switched to these and then they turn out to have some other nasty problem we didn't know about, or that the regulations have been drawn in a way that's full of loopholes again and gets exploited. Hence, wanting to show, let's do almost an untargeted analysis of what pollutants are coming in. Can we find anything that's really bad, on the one hand? And then the second bit about testing the provenance to make sure that the CO2 reductions are genuine. So that's so Andrew, I think it's a very good point from the angle you're coming, but what I'm showing in the presentation is for another ultimate objective. But it's a good point nevertheless. Is it feasible that vehicles could detect if they are running on e-fuels or conventional fuels? Now, I probably on this should defer to an engineer who knows more about it than I do. The only comment I can usefully make on that is that when we've in the past done separate testing on ethanol blends in gasoline, we have seen particularly on more sophisticated vehicles, automatic changing of ignition timings and other adaptations where it's only the blend of fuel that has been changed. So over time, the engine management seems to have adapted to this new fuel. Now, whether that's done it by, in some sense, sensing the composition, or more likely looking at the characteristic behavior of the engine that might reflect a change in fuel, I think that second is probably more likely. But I'm not going to go much further than that without getting into trouble with real engineers who I'm sure can comment more. But it is a very good point, because you want the vehicle to be operating in a way that makes most use and gets most energy out in the least polluting way from that fuel. Okay, so we're running gradually towards the end of time. I'm just scanning to see if there are any final questions. Please do keep any last ones coming I do remember, actually, there was a question right up top, I think, about the effect on the emission or renewable fuels. We should look much more about what effect they have on the after treatment system, the catalysts and filters in the car, rather than thinking about the combustion process. And I think that is an absolutely fair point. And it does speak to questions around, what is the short-term effects of a change in fuel, and what's the longer term effects in terms of catalyst degradation or filter blocking or whatever it is. What I would say is this sort of method with 2DGC is actually really helpful if we're trying to spot hallmarks of issues developing with catalysts or filters. We can look for these individual species in the exhaust gases that might be evidence of a problem developing, or to help diagnose the cause of a problem that has already happened. And thank Bradley for the question. Was there any analysis performed looking for the presence of catalyst compromising compounds in the renewable fuels, particularly HVO? Actually, in this particular case, no. But actually, it's a very good point. We'd be interested to do that, and maybe that's something we can discuss offline, because we do have the complete compound list for each HVO, and also the accompanying tailpipe emissions as well. So that is data that's in our database that we can go and interrogate. So, any last questions coming in? Just looking up the list, make sure I haven't missed anything. Well, I promise you I will have missed something. It's not personal or intentional. Klaus, they've got a question. Are we planning to look at e-diesel and e-gasoline? Yes, absolutely. Absolutely, we are. And as it stands, I don't have anything yet which is that I can publish. But it is certainly from a tailpipe emissions point of view, the hypothesis is certainly, that these should perform significantly better. Say, a pure methanol to gasoline. The issue is more about understanding, is there any way of using that to try and understand the provenance of fuels? So if we were ever shown a blind version of an e-gasoline, would we be able to tell anything about the quality or the nature of the production process? The closest we have done historically, we have looked at things like gas to liquid diesel as well, and looked at the effects on CO2 emissions and pollutant emissions as well. So in a sense, we're working our way gradually from the standard sort of E5, E10 right up now. We're working towards understanding these purest forms of synthetic fuel, and it certainly has become a very hot topic. And reading the way the smoke signals seem to be going, it may well be that a lot of focus will come on e-fuels very soon. There's a question, what's the actual price of these e-fuels and what could be the potential price by 2035? At the moment, they're very expensive. I think that the figures I normally read quoted is something like €5 per litre, which makes it, 3 times or so more expensive. But it's not just that, it's the volumes produced wouldn't allow mass rollout now, even at that price, even at any price. But that question as to what's the potential price by 2035, well, in the sense, it's a question of, will e-fuels survive at all in any mass sense? And that, to me, all comes down to whether we can scale and decarbonize the grid in time. And where I think a lot of policy effort and support needs to go is into accelerating that process more than concentrating on powertrain re-engineering, as seems to be the fashion of the day. If we can get a big scaled green grid, then things like e-fuels will not only become possible at scale by 2035, but hopefully then could be at a commercially acceptable price. If not, that's the market, and the right powertrains and fuels will probably win out in the end. But that building that scalable grid and probably requiring a significant proportion of nuclear is the only way that will happen in practice. So we need to get on with it. But the French managed to turn their grid nuclear in 15 years in the 70s and 80s. So it is possible. On that note, I will stop there. We are out of time. I want to finish on time. If I have missed your questions, I'd be very happy to pick them up offline. But thank you very much for attending. Value your time as ever joining us. And please do join us at the next webinar. Thank you again. Bye-bye.